Hello everyone, with you Ship ETO. Somehow, on the internet, I came across an interesting article about neuromorphic chips. I really liked this article because I didn't expect that neuromorphic chips are already among us, namely in household appliances and smartphones. And I began to study them in more detail. I was shocked by what I came across, but everything in turn. Let's start from the beginning, namely with a brief overview of the theory. What is the human brain and a neural network? The fundamental element of both the human brain and the neural network is a neuron. In the human brain, the main building block is a biological cell, a neuron. It receives signals from other neurons through dendrites, processes them in its body, and, if the signal is strong enough, transmits it further through the axon. In the neural network, there is an artificial neuron, which is a simple computing node. It receives numerical data, signals as input, performs a mathematical operation on them, and transmits the result further. Network structure, connections, and layers. In the human brain, billions of neurons are interconnected in a highly complex three-dimensional network. They form different parts of the brain that specialize in specific tasks: vision, hearing, thinking. In a neural network, artificial neurons are organized into transparent layers. Input layer receives the initial data, for example, pixels of a picture. Hidden layers, several layers where the central information processing takes place. Output layer gives the final result, for example, the answer. There is a cat in the picture. Information moves sequentially from the input layer to the output layer, undergoing processing at each stage. Signal transmission, synapses, and weight. In the human brain, the connection between two neurons is referred to as a synapse. The strength of this connection can vary. If the synapse is strong, the signal is transmitted more effectively. If it is weak, it is less effective. The change in synaptic strength is the basis of learning and memory. In a neural network, each connection between artificial neurons has a weight, which is simply a numerical value assigned to it. This weight determines the importance of the input signal. If the weight is high, the signal is amplified. If it is low, it is attenuated. The primary goal of training a neural network is to determine the optimal weights for all the connections. The learning process, experience, and mathematics. In the human brain, learning occurs through experience, repetition, and the formation of associations. This process, known as neuroplasticity, physically changes the strength of synaptic connections. When we learn to ride a bike, the connections between neurons responsible for balance and coordination become stronger. In a neural network, learning occurs using an algorithm, most often the backpropagation error method. The network receives a task, for example, recognizing a photo of a cat, and makes a guess. If the answer is incorrect, the algorithm calculates the magnitude of the error. Then it goes back through the network from the output layer to the input and slightly adjusts the weights of each connection so that the next time the error is less significant. This process is repeated thousands of times on massive datasets until the neural network learns to perform the task with high accuracy. That was a short theory, and now the most interesting thing is what a neural network is. A neural network is a computer system designed to mimic the human brain, enabling it to learn and identify complex patterns in data independently. Imagine it as a virtual expert that can analyze information, make predictions, and make decisions. We live in the era of neural networks and artificial intelligence. Platforms like ChatGPT or Gemini, which run on powerful, energy-hungry cloud servers, have captured the imagination of millions. But a quiet but equally significant revolution is taking place in the billions of devices around us, from smartwatches to industrial sensors. How can we equip these battery-powered devices with intelligence without depleting their limited energy resources? Two key technologies are making this possible: Edge AI, artificial intelligence, and neuromorphic computing. They bring computing from distant data centers directly to your fingertips, making intelligence instant, private, and incredibly efficient. What is Edge AI? Computing where it matters. Edge AI is the deployment of artificial intelligence models and algorithms directly on local devices with limited power, rather than in a centralized cloud environment. Instead of sending data to the cloud for analysis, the device processes it itself. This approach has fundamental advantages over traditional cloud AI. Ultra-low latency. Real-time data processing directly on the device is critical for instant decisions. Cost-effective. Eliminates the need for ongoing payments for cloud computing. High reliability. Continues to work even without a network connection, which is ideal for autonomous systems. Maximum confidentiality. Data remains on the device, eliminating transmission risks and ensuring security. As you can see, the benefits are enormous. However, they raise a fundamental challenge. How do you power a powerful AI on a tiny battery without draining it in minutes? The answer lies not in optimizing old methods, but in a completely new approach to computing, inspired by the most efficient computer known to man, the human brain. The human brain as a model, an introduction to neuromorphic computing. Neuromorphic computing is an approach to creating processors that mimic the structure and functioning of the human brain. Instead of mindlessly executing billions of operations per second like traditional chips, neuromorphic systems aim to achieve the extraordinary energy efficiency of the brain, processing information only when it is needed. This approach is based on two key principles. Spiking neural networks, SNN. Imagine a traditional chip as a drummer who beats a drum with a constant rhythm, a clock signal, regardless of whether there is a reason to do so. A neuromorphic neuron is a sentinel that only sounds an alarm, a spike, when it sees something important, a sufficient number of incoming signals. Because spikes are generated infrequently, the amount of data moving around the chip is significantly reduced, resulting in a dramatic reduction in power consumption. Event-driven computation. This spiking approach is the basis for event-driven computation, where the system responds only to meaningful information. The brain does not process the entire visual scene with the same intensity. It focuses on changes and motion. Similarly, neuromorphic processors like brain chips Akida use sparsity, i.e., the ability to ignore unchanging, redundant information and process only meaningful changes to focus on only the most essential data. They ignore unchanging information, avoiding unnecessary computations and saving energy at every step. These once theoretical concepts are now being implemented in real hardware thanks to pioneering companies. Pioneers hardware that brings edge AI to life. Different companies are offering unique approaches to building edge AI hardware, each with its own strengths. We'll look at two key methods: optimizing traditional architectures to the limits of power efficiency, AMBIC, and creating fundamentally new brain-inspired processors, BrainChip. AMBIC, the leader in ultra-low power. AMBIC is a leader in creating ultra-low power systems on a chip, SoC, i.e., full-fledged computers on a single chip, specifically designed for battery-powered edge-to-edge AI devices. Their mission is to put intelligence everywhere. Key technology: proprietary sub-threshold power optimized technology SPOT platform, which allows chips to operate at extremely low near-threshold voltages, significantly reducing power consumption. Product example: Apollo 510 SoC, which delivers 30 times more power efficiency than previous generations and can process complex models for speech recognition, vision, and health analytics. Key benefit: enables always-on functionality in power-constrained devices such as wearables, smart remotes, and smart home gadgets. BrainChip, a true neuromorphic approach. BrainChip is a pioneer in the commercialization of neuromorphic technologies. The company licenses intellectual property, IP, i.e., ready-made blueprints of processing units that other companies can embed in their own chips, for AI accelerators, based on more than a decade of research and development. Key technology: the Akida processor, which uses event-based processing to achieve efficiency that is 100 times higher than conventional approaches. It is optimized for sparse data, weights, and activations, allowing only the critical information to be processed. Product example: the Akida processor IP block, which can be integrated into any chip to accelerate AI. Example: voice recognition. One of the most famous examples is the use of Akida in the Mercedes-Benz Vision EQXX concept car. The chip enables the Hey Mercedes function, consuming significantly less energy than traditional solutions, which is essential for increasing the range of an electric vehicle. In-cabin monitoring, detecting driver fatigue, identifying passengers, or recognizing gestures to control vehicle systems. Thanks to the low power consumption, the system can operate continuously. Driver assistance systems, ADAS, integrating and processing data from various sensors, cameras, radars, to quickly detect obstacles, pedestrians, and other vehicles. Main advantage: allows AI tasks to be performed in real time, consuming only milliseconds of power. This is ideal for processing audio, keyword recognition, and video, object detection directly on the device. Why is this important to us? The combination of ultra-low power consumption, high performance, and affordability creates a massive field for innovation. For students, early-stage developers, and inventors, this means that powerful AI is no longer the preserve of large companies. Here are just a few of the exciting applications that are becoming possible. 1. Truly smart, always-on sensors. Imagine a smart doorbell that lasts up to 18 months on a single charge, instead of reacting to any movement, such as a flag flapping in the wind or a car's headlights. A neuromorphic chip, like one from Inatera, uses radar to accurately detect people by analyzing their body movements as they breathe, even when they're standing still. This is the true always-on paradigm. The device is constantly analyzing its environment, but only uses power when it matters, as opposed to continually streaming data. 2. Personalized and confidential devices. Wearable health monitoring devices, smart glasses, or hearing aids can analyze your biometric data or surroundings in real time. Since all processing takes place on the device, your personal data never leaves it or is sent to the cloud. This ensures complete privacy and security. 3. Accessible AI for everyone. With low-cost boards like the Cypid Makes based on the K210, anyone can start experimenting with computer vision. You can create a system that recognizes objects, faces, or even classifies handwritten digits without having access to expensive servers. This lowers the barrier to entry in AI development, allowing you to bring your ideas to life quickly and at minimal cost. The world of edge AI and neuromorphic computing is just beginning to reveal its potential. Starting your journey in this field today means becoming an architect of the next technological wave. How can neuromorphic technologies be used on modern ships? Autonomous navigation and collision avoidance systems. This is probably the most promising area of application. Modern ships generate vast amounts of data from radar, LIDAR, sonars, and cameras. Neuromorphic systems can process this data stream much more efficiently. Neuromorphic event vision. Instead of traditional cameras that capture full frames, dynamic vision sensors, DVS, are used. They react only to changes in the field of view, similar to the human eye. This enables the instant detection of moving objects, such as other ships, buoys, or drones, even in challenging conditions, fog, night, while ignoring the static background and significantly reducing computational load. Faster decision-making. With low latency, neuromorphic chips can assess collision risks more quickly and adjust course in real time, laying the foundation for the development of fully autonomous ships. Sensor fusion. The architecture of neuromorphic chips, often based on spiking neural networks S and N, is ideal for combining disparate data from many sensors into a single coherent picture of the environment. Predictive maintenance and system monitoring. Unexpected failure of engines, generators, or pumps in the open sea is expensive and dangerous. Neuromorphic technologies allow for the transition to proactive maintenance. Anomaly analysis. Neuromorphic sensors can constantly listen, acoustic analysis, and feel, vibration analysis, the operation of the engine room. They learn to recognize the normal state of the equipment. Early detection of faults. The system instantly detects the most subtle deviations from the norm, signaling potential bearing wear or fuel system problems long before a critical failure. Edge computing. Thanks to ultra-low power consumption, these chips can perform deep analysis directly on the equipment without the need to constantly transmit large amounts of data to a central server or shore. Energy efficiency and route optimization. Reducing fuel consumption and emissions is a crucial task for the shipping industry. Power plant optimization, neuromorphic systems can analyze thousands of parameters, weather, waves, currents, and ship loading, in real time and adaptively control the operation of engines, trim, angle of inclination, and ballast systems to achieve maximum fuel efficiency. Adaptive planning. The system's fast processing of meteorological and oceanographic data enables it to constantly adjust the route, avoiding storms and capitalizing on prevailing currents. Robotics and inspection. The use of aerial drones and autonomous underwater vehicles (AUVs) is increasing for inspecting ship hulls, propellers, and cargo tanks. Autonomous control, neuromorphic chips are ideally suited to control these devices in complex, dynamic environments. They provide high-precision maneuvering and a fast response to obstacles with minimal power consumption. Automated inspection, drones equipped with neuromorphic cameras (DVS) can effectively detect corrosion, microcracks, or coating damage in real time. Security and cybersecurity. Surveillance. Neuromorphic vision systems can effectively monitor the perimeter of a ship to detect atypical activity, such as the approach of small boats, a piracy threat, or unauthorized drones, with a low false positive rate. Cybersecurity. As digitalization increases, ships are becoming more vulnerable to cyber attacks. Neuromorphic systems can analyze network traffic, detecting new, previously unknown threats faster than traditional security systems thanks to their to recognize complex patterns. Neuromorphic technologies on ships combine high performance in artificial intelligence tasks, real-time learning capabilities, and ultra-low power consumption. This enables safer, more efficient, and environmentally friendly ships. What do you think? How soon will these technologies be implemented on ships, or have you already seen them in use? Write your opinion in the comments. Don't forget to subscribe to the channel and hit the like button. See you later.